Now, first question here comes is what is low power? Why low power? So I ask why low power? Why we need low power design? What is the main reason behind using this low power? Because anyway, let's say in our circuit, there is a chip in our design, okay? Some chip in our design, which is inside some SoC or there is some microprocessor or whatnot. Okay. So what will happen is this chip will consume some power. There is some VDD or VCC is connected to this chip. So this chip will take power, right? And when this chip is computing something, it will take power directly from this VDD. But let's say there are millions of gate. Okay, so this VDD directly from the voltage source will come to some particular block of that chip that is computing something. So it will trace some long path. So there might be possibility that these path will take some power, and there might be loss of power. Okay. Okay. So due to this loss of power, it might happen this complete VDD will not reach to this particular thing. Okay. So in this case, there are power losses as well. So what you can directly do is you can increase this VDD. Okay. Let's say you want this VDD here to reach is 5 volt. Okay. But due to losses, it is reaching here as 4 volt only. So what you can do is you can make this VDD equal to 7, maybe 6 volt, and it will reach till here. After losses, it will reach here by decrease by 1 volt and complete voltage will reach here is 5 volt. But that is a solution of the problem. But that is avoidance of the problem, not solution. Because what will happen is these old parts of the chip, the other parts of the chip are consuming power, which is not desired. Because they are anyway giving some type of loss to us, right? They are giving us some type of loss. We don't want that loss. Okay, so what will happen is instead to make these power losses minimum, what we did is we did packaging. Let me write it here. We did what packaging and cooling cost. So what we will do is we'll provide a good packaging to that source so that the enough power that is dissipated should not harm our chip. Okay, so for this, what we'll do is we'll provide the packaging and the cooling. This is cost. Okay, so what do this packaging and cooling cost means is? Okay, so that means is high power dissipating in path leads to higher packaging and cooling cost. It means with large power to my chip, it means I need to provide a good packaging as well. I need to providing cooling as well. So, but since we are providing these packaging and cooling to this, so this is increasing the incremental cost in the design. Incremental cost in the design. So it is basically enhancing the cost, which we don't want because we want to produce the chip on mass level. Okay, because that will be going to the market and in each device that chip will going to be used. So in that case, if what we want is we want that chip to be economical. So if we are providing like unnecessary power, like according to what we want, okay, then there will be lot of power dissipation. Due to the dissipation, the temperature of the chip might to go high, and this will lead to failure of the chip and anything. So to like due to these higher dissipation of power, what we need to do is we need to provide a proper packaging. And since there is lot of power dissipation, then we need to provide the cooling environment as well. So let's say in your laptop you might see some fan is there, exhaust fan is there. So what they are doing is they are providing some type of cooling. Okay, so it means you need to do extra invest on the packaging and as well as the cooling. Okay, so so that will increase the cost and we don't want that cost. So that's why we require low power. This is the one point. The other point that can be, so what our goal is, why low power? Why low power? Okay, the other point is we are increasing the power density. Increasing the power density. Okay. Now increasing the power density means, so since as we are going into the tech node, So if you know Moore's law, so we are going into deep nodes, right? So tech node is what? Tech node means size. So since we are going to the deeper tech nodes, it means size is going to decrease. Now, since the size is going to decrease, so what will happen is the power density of VLSI chip will increase. Okay, so the power density will increase because size increase. It means in the less area we can compact more and more CMOS, right? So it means power density increase, size decrease. It means power density increase. Now, since size decrease and power density increase, so what will happen in a chip is there will be lot of power spots. So there are lots of power hotspots. Okay, there will be lot of power hotspots. Then what this power hotspots will do again, since there are due to the power density increment, there has been more of power hotspots has been created. So that will lead to the design failure sometimes sometimes whenever the power increase or the chip get effect from all those things, right? So that's why we want to use the low power, right? Third point I can say is reliability. Reliability. Now let's say if I give you a simplest example, okay, if I'm saying you the if I'm increasing the temperature, let's say, okay, if I'm increasing the temperature, if the temperature is increased, what will happen is there are chances that the wire nearby can melt, and there are chances that though due to that melting thing, there can be short circuit and open circuit, and that can lead to the failure of the chip. Okay, there can be anything. So previous data states that every 10-degree increase in the temperature, every 10-degree increase in temperature, okay, reduce reliability by 50%. Now you'll say how? Okay, so this the data set. Okay, since we are increasing the temperature due to the dissipation, there is a whole increment in the temperature. So due to that, reliability is decreasing. Now, same example, if I give you one more example, let's say your laptop, you are working on your laptop or your mobile smartphone. Okay. Now, let's say one of you is sitting in let's say Kashmir, okay, where temperature is around 0 degrees Celsius. Okay. And one of you is in, let's say one of you is in Rajasthan. Okay. Where temperature is around 35 degrees Celsius. Okay. Now, both of you are using the same phone. It means same chip is in there. Okay. Now, your chip should be in that way ki it should tolerate this temperature as well. But since this 0 degrees Celsius is a good temperature, that is a cooling atmosphere for its chip, right? So that won't affect much thing. But since the same smartphone, or maybe you went for a vacation in Kashmir, then came again to Rajasthan, like you are from Rajasthan, let's say something like that, like somewhere where temperature is higher. Okay, so let's say it's 40 degrees Celsius. It means the same chip should work at the 40 degrees Celsius as well. Okay, it means reliability should be same throughout the, right? It means environmental impact should not affect our chip, right? Environmental impact should not affect our chip. Okay? This environmental impact should not affect the chip. So that is one thing, right? So these are the necessity for low power design. Because these factors are the necessity for low power design. Okay? You understand? So this is our motivation to start to go through towards the low power design. Okay? Now, now we will say, now we'll say power dissipation. Power dissipation, that is the main motivation towards low power design. Now we'll say how these power dissipation happen. What are the sources of this power dissipation? What are the sources of this power dissipation? So there are mainly two sources of this power dissipation. That is dynamic power and static power. Now you'll say, what is dynamic power? So what is dynamic power is dynamic power comes under picture when your chip is operational, when your chip is operating. So whenever your chip or your circuit is in operation, then what will happen is due to the charging and discharging of capacitors, okay, due to the charging and discharging of capacitor, there is a power switching. Okay, so due to which glitches occur, due to which undesired transition or spikes from gate delay can occur. Okay, so that leads to the dynamic power. Okay, then there comes this static power. Now, what do you static power is? Static power is when your chip is not operational, when your chip is in at standby. Let's say you are working on your laptop. Now you made it to sleep mode or you shut it down. Okay, and went for, let's say, playing cricket or playing games, playing sports, something. Okay, now when you left your laptop, the battery percentage is, let's say, 90%. Okay. Now, when you came back after playing your sports, you saw your and you restart your laptop and you saw your battery is getting is around 70 or maybe let's say 60%. It means 30% battery has been lost. Why? Because of the static power. Because when your laptop is not operational, still 30% of the power lost. Okay. So that is the static power. When you are not working on your laptop, but due to some static power losses, your battery went to 60%. Okay. And why that occur is that, okay, since whenever you left your laptop like this, okay, it won't happen because there are low power dissipation or low power circuit techniques already employed in your laptop. So it won't happen until and unless your laptop got out. Okay. So what are these region of those static power? So there are diode leakage, there can be gate leakage. Okay, there can be sub-threshold leakage. Okay, and many more reasons. So we'll see all things in detail. I'm giving you the overview why we are towards low power designs, VLSI circuits. So in the coming lectures, we'll see all these things in depth. Okay, now we will say since power dissipation is depending all those parameters. What are those parameters? Those parameters are supply voltage. Okay, that is VDD. Okay, then we'll say capacitance. In each NMOS CMOS circuit, we have capacitance related to each. Okay. We have switching activity, that is alpha, let's say. We have threshold voltage of NMOS CMOS, that is VTH. So we have all these parameters. Okay. So we have all these parameters. Now these parameters are means power dissipation depends on these parameters mainly. Now let's say you want to control this power dissipation. It means you have to make these parameters as controllable. Okay. If anyhow you can control these parameters, then you can say we can control the power dissipation. Okay. Now, if we go toward the basic approach of low power, basic approaches towards low power, then what do we? We'll say we need to minimize what? Okay, since power is C VDD square into F if you consider it. Okay. Okay, that is for energy or something, let's say half CV square, that is CVDD square, something like that. So it means this power dissipation is depending on capacitance. It is depending on the supply voltage VDD. Okay, and similarly, this capacitance and all those things that depend on. Acha, okay, this power dissipation is equals to alpha C VDD square, where this alpha is the switching rate. We'll come to all those things, how this formula came, and we'll come to those things. Okay. So this alpha is the switching. This is the switching activity. This is the capacitor and VD is the operating voltage. Okay. So we need to do what? So basic approach toward this is we need to minimize the switching capacitance. What? Minimize the switching capacitance. Minimize the switch capacitance. Okay. We have to minimize what? Minimize the leakage power. Leakage power. We need to scale this voltage. What we can do is we can supply voltage scaling. How do we do that? We'll see. Okay. Okay. Let me tell you this. Okay. What do you mean by this supply voltage scaling? What do you mean by this supply voltage scaling? I'm giving you the overview. In depth, we'll see. Okay. Now what this supply voltage scaling is? So we know this VDD is the critical parameter. Critical parameter. VDD is the critical parameter. Okay. And this power depends on the VDD square. Power depends on the VDD square. It means VDD is a critical parameter, then VDD square will be more critical, right? Now, if somehow we reduce this VDD, if somehow we reduce the VDD, then what will happen is power will reduce, and that is our ultimate goal. Ultimate goal. Okay. If we are reducing the VDD, then power will be reduced, and that is our ultimate goal because we want low power design circuits. And we have to design our circuit in such a way that at low VDD, we can operate our circuit. Okay. Okay. So ultimate goal is lowering the power dissipation, and what do we want is we want our circuit to operate at low voltage. Okay. But it's not directly that easy. If you are decreasing the VDD, the delay will increase. Delay will increase. And since delay is increasing, it means circuit will take time to give you the results. Let's say let's say you have a AND gate. Okay, the input is 1 1. So the output you are getting is at 1 only. Or let's say your input is 0 1. So your output is 0 only. Now you have changed your input, that 0 is changed to 1. It means now input of the AND gate is 1 1. Okay, so output should be, let's say you have this AND gate. Okay, you have input A, B, and output Y. Okay, now what happens is, let's say input is 0, 1. So output is 0 only. Okay, let's say input A is 0, B is B is 1 only, something like that. Okay, and Y is something like that. Since it's 0 and it is 1. Okay, so let's say output is 1 here. Oh, let 0 here because this is AND gate, right? So output is 0 here. Now at this point, you did what? You change the voltage. You change the voltage from 0 to 1. So now what will happen is this A is at 1, B is at 1. So output should change to what? Change to 1 only. And ideally it should change here only. But it will take some time and come here because we decrease the VDD. What will happen is in this circuit, we decrease the VDD, And since VDD is decreased, the delay has increased. Delay has increased. So the switching speed will come little later. Okay, so if you see at the broader level, in a chip level, you can see this is a glitch, right? This is a glitch, and that can make unwanted changes in your circuit. That can affect the operations of your circuit, and that we don't want. So we want our VDD to be decreased and delay should not go high, right? Right. So what we have to use some different technique that should take care of these things. So let's say you are using some voltage scaling approaches. So what will happen in your design or in your chip, there must be some different blocks or there must be some subsystems. Okay. And what we can do is instead of providing every block as a fixed voltage, what we can do is we can provide them at different voltages. And those voltages will be determined at the design time according to the functionality of the circuit. Okay, so that technique will include device features, that is size scaling. We can provide different parallelism, okay, for low power, and we can provide pipelining. So what are the important thing? Important thing are parallel. Important thing is pipeline. Okay, we'll see how these are the important concepts: parallelism and pipeline. Then we can do the multi-level voltage scaling. So what will we will do in the multi-voltage scaling is, so multi-voltage scaling is basically the extension of static voltage scaling. Okay. Where what will happen is where your VDD is switch between two or three or more fixed voltages. Let's say your VDD is somewhere it's VDD, somewhere it's zero point 0.5 VDD. So depending on the, let's say you are doing the addition operation, then you'll use the zero point 0.5 VDD because that won't require that much energy. And whenever you are using the multiple operation, then you will use the VDD. Okay. So what will this multi-level voltage scaling do is it will switch between two or fixed few voltages at different instance of time. At different instance of time. That means whenever you are doing addition, you will use a different voltage. Whenever you are using a multiplication, you will use a different voltage depending on the design or depending on your use case. Okay. Then there comes this DVFS technique. This DVFS is dynamic voltage and frequency scale. What is this? Dynamic voltage and frequency scaling. Okay, so it is again the extension of the MVS technique. So what will happen in that is here large number of voltage and frequency pairs are dynamically applied based on the workload. So based on the workload, you will provide what? You will provide different voltage and frequency. Okay. Then there will come say adaptive voltage scaling. So what was the DVFS? Will like we will have a large number of voltage and frequency pairs, and those are dynamically applied based on the workload. And in adaptive voltage scaling, what we'll do is it is again extension of DVFS where we have a closed loop system. So in adaptive voltage scaling, we have a what? Closed loop system. Okay. That closed loop feedback system will be on the chip and it will keep on monitoring. It is on chip and keep on monitoring. Keep on monitoring. Okay. So according to what workload design is working on, it will do what? It will adjust the VDD. Adjust VDD and frequency depending on workload. Okay. Okay. So these are the techniques that we will be going to look at. Then, then we talk about the switch capacitance, minimizing the switch capacitance. Minimizing the switch capacitance. Okay. So what will happen in minimize? How do we like minimize the switch capacitance? What will be the techniques to reduce dynamic power dissipation through minimizing the switch capacitance? So there we need to check for the hardware software trade-off. Hardware software trade-off. Okay. So what will happen is we will judiciously partition between the functionality. Okay. Because hardware is faster. Hardware is what? Faster, but use more power. And software is what? This is slower, but use less power. Okay. So depending on those things, we can divide functionality between hardware and software. Okay. So that is the one thing for hardware software trade-off. We can use the bus encoding. We can use the bus encoding. So what is that bus encoding is? So whenever you are communicating data in form of, let's say, gray code, inversion coding, binary coding, something, then we'll reduce the total number of bit transition. So what we'll do is we'll reduce the total number of bit transition. Bit transitions. Okay. Then we have to see for what? We have to see for glitch minimization. We have to see for glitch power minimization. Then how do you see for the glitch power minimization? So we know glitch power minimization. It means we can use the clock gating. So what do you mean by clock gating? Since
Sir, that glitch power is the ripple spikes. It is coming. That is called glitch power or a different thing?
sorry,
Glitch power and short circuit power is same or different actually, sir?
glitch power is that is spikes coming into the your waveforms. Let's
Okay,
say
okay.
you have a circuit. Okay, let me tell you one thing. You have a
What is the
circuit.
reason for that spikes actually?
Yeah, yeah, we'll come to all those things. I'm giving you overview in this session. Please have some patience. Okay, I'll come to each things in detail. Okay, so let's say you have a circuit. You have a clock. Okay, you have a clock like this. Okay, now this particular circuit is working on the positive edge. Okay, now let's say there is some spike here. Okay, that spike will be a positive edge for this circuit, right? Right. So what will happen is this circle will start working because and it will sample data at this edge. Okay, but this is unwanted. This is unwanted, right? This is unwanted. We don't want it. Correct? Since this is unwanted, we don't want it, but still our circuit is operating due to this glitch power. So what we need to do is, or let's say you have this thing. You have your circuit. Okay. Your circuit is not doing anything because there is nothing coming up. Okay. Or let's say this particular part of the circuit, this is some block A. Similarly, there are some multiple blocks as well in your circuit. Some big circuit is there, and there are block B, block 3, block 4, something like that. This is block 1, let's say. Okay. So if particular signal, let's say one enable, okay, enable will come, then only this circuit will work. Okay, otherwise the circuit won't work. No, let's say enable is 0. Okay, enable is 0, but still clock is going to that circuit as well. So what will happen is this circuit will keep on, like it will take some power. There will be some dissipation. Okay, so what you can do is you can use this enable signal and provide gating to clock, because if clock will not go to this circuit will not switch. Okay, so what you can do is instead of directly providing the clock, you can provide enable signal and with your clock, right? So whenever enable is 1, then only this clock will go to this block A. Otherwise, whenever enable is 0, there is no toggling at the clock edge. The clock will not go to this circuit. So it's not directly good to directly use this AND gate only. We'll see like latch based technique is there, so that we will see. That is the concept of clock gate. So what we are doing is we are dynamically preventing the clock from propagating to unused parts of the circuit. So since this block A is the unused part of the circuit when this enable is 0. Right? It will be part of the used part of the circuit when this enable is 1. So what we can do is we can dynamically prevent the clock from propagating to this block A. And we'll suppress the unnecessary transitions. So unnecessary transition can be suppressed when this enable is 0. Okay, how? Using the clock gate. Okay, and we can implement all these things at the module level, register level, or we can implement that at register cell level. Okay, then let's say you have your FSMs. You have your FSMs. Okay, in that FSM, in those FSM, what will happen is there might be some different encoding is used. Let's say you are using some encoding 100, 101, 110. So if you see 0 and 1, these bits are toggling, then 1 and 0, these bits are toggling. It means there are two toggles. So you can use gray coding, something like that. Only one bit toggling is there in gray code, subsequent bits, right? So you can employ those state encoding techniques as well. So what will happen, say, in this the finite state machine, your FSM, will use your state variable in such a way that it will minimize the bit transition. It will minimize the bit transition when we are moving from one state to the other state. Okay? And this will reduce the dynamic power. Because let's say you have a 000, next state is 001, let's say. Next state is 010. Now here you can see there are 2-bit flip going from one state to two state, from this state to this state. If you have used the gray coding, then what will happen is 000, then 001, then 011. So this is the next state, right, in gray coding, and you will say only one bit is flipping. It means what we can do is we can provide encoding to minimize bit transition when moving between states, and that will reduce the dynamic power. Reduce the dynamic power, right? Right? Then you have leakage power reduction as well. You can provide the leakage power reduction. So for leakage power, whenever this leakage power term will come, okay, so leakage power is always associated with VTH, because whenever your device is like something like this, from source to gate, something like this, there are some power dissipation is there. Okay, so that power is the leakage power that we'll see. So we can reduce that leakage power through this VTH value. So as we decrease this VTH, okay, your leakage power will reduce, but delay will increase. Like switch will take time. Okay, and it will also increase the sub threshold current as well. Okay, so there we need to see how we can do it. So we can stack, like there are some techniques we can, what we can do it, we can use the transistor stacking. Transistor stacking. We can use the variable threshold CMOS and MOS. Variable threshold device. Okay. Okay, similarly, we can use, there are some other like power gating and all and whatnot, power gating circuits. So how we'll do those things, we'll see in details. Okay, later. Okay, so this is about the leakage power. Similarly, there are battery driven system designs in our SAM. Okay, so in our system, so those are the main reason we are studying the low power design and we are going towards the low power design. So now you will see what's the primary motivation for designing the low power circuit. Primary motivation for the low power circuit. So what we can conclude is if we want to reduce the cost reduction. So what will happen is low power dissipation, it will reduce the cost associated with the packaging and the cooling of chips. Then we want to manage power density. Okay. So second is managing power density. Right. So whoever saying this MOSFET symbol is wrong, so don't go into this symbol. I just wrote it that way. Okay. Okay. So we are saying about managing power density. So what does that mean? Is managing power density mean? So what we are saying is when we were talking about this power density, we were saying what? Ki we are reducing the size. So as device size decreases, as device size decreases due to the tech node or due to the move slow, right? So power dissipation is increasing, or that will lead to the hotspots. Okay, and which low power design helps over. So increment in hotspots, increment in, please don't say this increment spelling is wrong. Okay, increment hotspots. Okay, so what will happen is there is increment in hotspots. Okay, so how do we avoid them? Using low power design, using low power circuits. Okay, then let's say we have battery operated device like our laptop only or your mobile phone only. Okay, and what do you want is whenever you turn off your laptop, you don't want your battery to get drained. Okay, so what you will do is, so there are these power getting circuits, there are these clock getting circuits already employed in your chip. So those will tell the system to not to use that clock or not to use that power. And that will help in limiting the power dissipation. Okay, then there just comes this reliability. So we saw every 10-degree rise in the temperature reduce the circuit's reliability by 50%. We don't want that. So that's why we want the low power circuit. Okay. So the power dissipation due to this processor. Okay. These, like if you see at the you go at the data center level. So if you see at data centers, there are a whole lot of data chips, whole lot of power dissipation is there. Okay. You will see like some 10 floors of a building are just data centers only, and they will require cooling, ACs and whatnot. Everything they will require. Okay. So it will take a whole lot of what? Whole lot of power. Okay. And it will impact your environment as well. And you don't want your circuits to dissipate that much power. So for environmental perspective only, for sustainable perspective also, we need low power designs. Okay, and we need to evaluate like the evolution should also not affect our design. Okay, so as fast we are going into the low power node, we want our circuit to work as that fast only at low cost power. So we want that also, right? Right. So those are the main things that lead to the motivation towards towards what? Towards low power design. Okay. Then we talk about the dynamic power. What is dynamic power? Ki whenever your circuit is working and your inputs are changing, right? Okay, your inputs are changing, your output is changing because of the clock, like, and clock is also applied there. Okay, so that time we have switching power, short circuit power, and glitching power. So those will be there, right? So whenever your inputs are changing, your output is changing, it means the capacitance will also change. How it is changing? The capacitance charging and discharging is there. Okay, okay. Then when you are saying ki your NMOS is working and PMOS is not working, because these are com- invert of each other, right? For the same input. So what will happen is, let's say your PMOS is like usually connected with your this VDD. Okay, so when your PMOS is, let's say, 0, it will trigger this path as the 1, and this path will be directly connected to output. Okay, so you will get a direct VDD to Y path. So there might be some dissipation here as well because of the short circuit power. Okay, then if it is a PMOS. Similarly, if it is an NMOS, so there might, what can happen there is, there will be ground is there and then it is connected to Y, something like that, right? Then due to the undesired transition or spikes, due to the gate delays and anything, there can be glitching power as well. Then, so these are the part of the dynamic power. Okay. Then for the static power, we saw कि power is dissipating when the circuit is in the standby mode. So even though your circuit is doing nothing, but still the power is dissipating. So that is your static power. And that those static power happen due to the cause of leakage current, diode leakage current, gate leakage, anything. So these are the main reasons that lead to, for the motivation of what? Motivation of what? Low power design. Right? Right? Okay. Now, in the future classes, how do we go through in this course? So we'll talk about these, whatever I discuss now, that we'll see. So what we will see is, we'll see the voltage scaling. We'll see the voltage scaling. Okay. Then how this voltage scaling depends. And voltage is scaling in presence of electric field. In presence of when electric field is constant, because you need to take care of all the, okay, electric field means voltage. Okay, so you need to take care of, right, when you are doing this scaling, what are the impact when the voltage is present there, when it is absent there. Okay, and remember one thing always, delay, you need to take care of this thing, because delay is directly proportional to your performance as well. If delay is increasing, it means your performance will decrease. Okay, that will be VDD minus VT. Okay, so that thing you need to remember, your delay is directly inversely proportional to VDD and VT. If you are increasing the VDD and increasing the VDD, then your delay will what? Delay will decrease. Okay, okay. And if let's say, okay, this is the important thing that I need to discuss. And let's say VDD minus VT, or I'm taking the case when VT is constant. Okay, now when I'm decreasing this VDD, it means delay will increase, right? Now, one thing, if I say you, instead of directly operating on the VDD, if I say this difference of VT, if so, what I want to do, my ultimate goal is I want to design the low power circuit. It means I want to decrease my VDD. So if I decrease my VDD, okay, and increase my VT, okay. So let's say one thing you. So delay is there. What I'm saying is my VDD is 1 volt. Let's say 1 volt, and VT is my, let's say, 0.5 volt. 0.5 volt. That is a normal scenario. Normal scenario. Now, and okay, what happened to this? So what value will come out of this? This will come out to 2 value. Okay. Now what I want is, I want to decrease my this 1 voltage. If I decrease this 1 to, let's say, 0.8. Okay. 0.8 minus 0.5, what will it be? What will it be? 0.3, right? 1 upon 0.3, that is 10 by 3. That is something 3.33. It means my delay got increased. Delay increased. Right? Similarly, if I say my delay proportional to, instead of 1, I made it as 1.5 volt, then it will be zero point 0.5. So that will come out as 1 only. It means my delay is decreased. But what do we want? Is we want to decrease the VDD. We don't want to increase the VDD. So what extra thing we can do it? Okay, what happens to this? So if what I do is, let's say when I'm making this at zero point 0.8 VDD, zero point 0.8, I'm decreasing the VDD. What I can do is instead of using this zero point 0.5, if I somehow make a low VT transistor and make this as zero point 0.8 minus made this zero point 0.5 as let's say zero point 0.3 VT, then what will happen is it will be zero point 0.5 only. It means my delay will be that only. So when I'm reducing the VDD, same time, I'm also doing what? I'm doing the reducing the VT threshold voltage as well. So if I'm reducing the voltage VDD, then I need to decrease my VTH as well, because that will then make this particular VDD minus V2 ratio as subtraction as the, or maybe difference as the constant, and that will not impact the delay. So you have to take care of all these parameters. You have to consider all these parameters, and then you need to design your circuit. That will help. You understood? Because if we are decreasing something, we need to. So there are basically trade-offs. So you need to meet all the trade-offs. So one trade-off is this VDD versus VT. Other trade-off is VDD versus delay. Okay, and how you are tackling this? If whenever you are decreasing the VDD, you are decreasing the VTH, right? So this is how. So at cost of something, you have to pay something. Okay, then only you get something. So that is how you work. Okay, then we are seeing ki when we are this reducing the supply voltage, how that architectural approach will make sense in your circuits. So we'll use the parallelism. We use two parameters, two thing, two most important thing. One is parallelism and other is pipeline. How do you do it? How do we do it? That we'll see. So let's say if I take the example of pipelining only. So what I can do is, let's say I want to use this 16-bit adder. Okay. So I'll give an input of 16 bits, give 16 bits, and then take a output C of 17 bits, let's say, or maybe 16 bit with a C out, or let's say it's Y, something like that. Okay. Okay. So what you can do is your 16-bit adder will obviously take much power because it is of like the depth and everything is more into this. So if it is taking the VDD power, what I can do is, or this 16-bit adder, let's say this is an adder, okay, it's taking some power. So instead, what I can do is I can pipeline these things. Pipeline what? Pipeline something like that. I use a latch here. Okay. So whatever the output or carry is here, so I'll divide them as A 0 to 7, B 0 to 7, and similarly there is input A, that is 8 to 15 is going in, and B 8 to 15 is going in here. Okay, now whatever the date, this is an adder that is 8-bit. So I'm dividing the 16-bit adder into the 8-bit adder. Okay, and I store that data here, some top bits. This is also a latch or maybe flop. Okay, and you can provide a 8-bit adder here. So in each cycle, to what you are doing, instead of doing this complete in one cycle, you are dividing that into two cycles. Then you can provide the remaining values here, and a carry also you can provide it here, and then you can get the sum value here. So this is how you can do it. So what we are doing it here, what we are, instead of like 16-bit addition, what we are doing is we are doing 8-bit addition, and we are performing that in each stage. Okay, so if you see in a 16-bit array, the critical path will be a long path. Okay, so instead of going into that long path, we are taking a 8-bit adder that will provide a shorter path. The critical path will be half of that, right? Right. So it means if I'm using that this circuit at VDD. Because if VDD is more, it will be a less delay, right? Then only it can work at some frequency F. So here what I can do is I can make this work at frequency, let's say F only at voltage VDD by 2. I can reduce the voltage here because here I don't need the delay that much. So that is what the pipelining thing is. Similarly, what I can do is if I want to perform much things, I can increase the number of resources. What I can do is in parallelism, I can use two 8-bit adder instead of one 8-bit adder. So this is parallelism. And then we can combine something and give our result. So that is parallelism. We will do, but in this case, we need to use the two resources. But here we can use only one resource only. In each cycle, we can use the same resource again. Right? Right? So there are trade-offs that we'll see. Okay, so we can optimize the size, we can do voltage scaling, we can do multi-level scaling, we can adjust the delay, we can adjust the power, we can do anything with it. But the ultimate goal will be low power. We need to achieve low power. We need to get the circuit operate at low power, at same performance, at same frequency, everything. Okay, then we'll talk about the DVFS, that is dynamic voltage frequency scaling. So dynamically we are changing the voltage and accordingly we are selecting the frequency. Okay, and always remember one thing throughout the course. Hardware is always faster than software. Hardware and software. Okay, so let me clear one thing. This hardware, these are faster, but these are costlier. Okay, and consume more power. On the other side, software, this is slower, these are cheaper, and this consume less power. This you always remember. Okay. So what we can do is, let's say you are running a processor. Okay, you are writing some instructions. Now your instructions, like your instruction will what? Will go, someone will detect, like let's say I've given one instruction, or maybe let's say I'm writing here something. But since I'm writing here something, but someone will sense those this writing and will give what? It means I'm giving input to this laptop, right? Or maybe I'm clicking somewhere. I'm giving input to this laptop. Now, how do this system will understand that? System will take that as a some 0000 encoding or some instruction, right? And those instructions will be understood by whom? Compiler. Then compiler will convert them into an instruction and give it to the hardware. And hardware will do what? The further things, right? So you need to remember, you need to uh, properly divide the task between the hardware and software. Those things, let's say, like for example, sometimes compiler is on the hardware, or sometimes compiler is in the software. Okay, so if you go in the RISC-V processor or 6 processor, so we'll realize that most of the complex tasks are done by the compiler in CISC, where in RISC most of the instruction set we are performing on the hardware only. So those are on basis of the hardware software trade-off and the power dissipation and all those things and whatnot. Okay. Similarly, we'll see what encoding we should prefer. Encoding. Encoding means is bus encoding, right? So that can be binary. We can use the binary encoding. We can use the gray encoding. Okay. Then we'll say when to use binary. So if you say in binary, you will see multiple transition from one state to other. But in gray encoding, from one state to other, you will see only a single transition. So there will be less power dissipation, right? Right. Okay. So that is one thing. Then we'll use the clock gating. In clock gating, let's say we have large number of unnecessary transitions. So what we can do is we can use the clock gating that will like delete unnecessary transitions. Okay. And in clock gating also, you will see clock gating based on AND gate, clock gating based on latch. So those circuits will go through. Then we'll see module level clock gating, register level clock gating. Okay, then what are the challenges in clock getting? So those things we'll see. Then you will also understood what are the challenges when you are doing the clock getting. Because when you are playing with the clock, two things will come into the picture. One is the clock latency, and other is the clock skew. So you need to maintain these things as well. So what do you mean by clock latency? So let's say whenever a single clock gate drives a large number of registers. Okay. Since this clock is driving large number of register, so this clock may not have enough drive strength. Okay. And it can require a clock tree at the output. So that is the clock latency. Similarly, if you talk about the clock skew, so let's say there are some glitches due to the maybe due to the some coupling or something, right? Okay, so since we have gated our clocks and everything, so there might be a glitch, and due to which we can receive the clock at the different edges. And since it is like, let's say here you are applying a clock and there is a gating circuit and you are getting clock here. Similarly, here also you are providing a gating circuit and you are providing clock. Now, whenever this clock is coming and this clock is coming, there might be some difference between the ages of these. So that is the clock skew. So that you need to take care about. Okay. Then we'll see the partitioning method, leakage power dissipation, kaise rokna hai, those things, power gating methods, and whatnot. Okay, then we'll see different types of power, where to use the lower VTS circuit, higher VTS circuit. Okay, so those things we'll see in the low power design. Then I'll tell you the industry perspective things as well. Okay, so that is the intro about our low power VLSI design course. From the next class, I'll give you the in-depth analysis of whatever we discussed. Okay, so this is about the today's class. I'm sharing my screen. If you have any question, you can ask me. We have 2 minutes, then I'll end the class. I hope you understood it. And I know you guys will have a lot of questions in your mind. Okay, have patience. All questions will be answered in this course. And if not, you can ask me. You can go through all this. And this low power design is very important from the industrial perspective. You will get a whole lot of good things. Those trade-offs, how to play with these trade-offs, how to do in the digital design, what circuits you will use, how do you use it. Those things we'll see. Okay. So I think this was a good class. We had a good understanding. If I have one question, sir, where can I get basics of low power design techniques? Your university course will suffice, right? You need basic digital designing, basic EDC and all those things. That is enough. Otherwise, all concept I will tell you. If you have doubts, you can ask me that time only. Basic digital, what you understood in your university exams. That is the only requirement. Anyone else? Any questions? Okay, then I'm finishing this class. Thank you, guys.
Thank you, sir.
Thank you. Thank you.
Rajit, do you have any question?
No, sir. No, sir. Clear.
Okay. Okay, then. Thank you.